Hello, welcome back. Another edition of Pre-Calc. We're on 2-2 polynomial functions. And our objective here is going to be to graph and analyze these polynomial functions, as you can see. All right, so let's just get rolling because less to cover. So if we take a look here at what a polynomial function is, these are the sums and differences of monomial functions. So now the next section is going to have a bunch of jargon. If n is a non-negative integer, let a sub 0, a sub 1, a sub 2, all the way down to like where it says here, n minus 1, and being the last terms in a sequence or a series. If they're all real numbers and the first one can't be equal to 0, then we can give this function here. Okay, so it's a lot of stuff. Basically, you're adding, subtracting different monomial functions. So this is called a polynomial function of degree n. And the leading coefficient, so we talk about it being degree n, and that leading coefficient is what we talk about, a polynomial function. And that is the leading coefficient is the one with the variable with the greatest exponent. So that's our leading coefficient. So in this example here, our leading coefficient is a to the n. I think it's got the greatest greatest exponent. It's a little easier to see and understand in real numbers when we actually use regular numbers here. But we can look at some graphs first. We take a look here, that a graph of a polynomial function, and then a non-example. So one of the examples over here on the left, the polynomial functions are defined and continuous. So we want to make sure we know that they're defined and continuous for all real numbers. So they're going to have smooth, rounded turns. There's not going to be any breaks. Okay, there's not going to be breaks, holes. So you can see these non-examples over here. These are non-examples, meaning that they're no good. These are not polynomial functions because they do not have breaks, holes, gaps, or sharp corners or anything like that. So these are not going to be polynomial functions. Okay, so that's kind of what the graphs are going to look like. So now let's talk about the leading term test. Okay, leading term test. So this kind of determines the end behavior of a polynomial function. So we look at here, the leading term test. That's going to determine the end behavior of a polynomial function based on the power and the sign. Power and the sign of the coefficient. Okay. So as we take a look at certain things in here in this table, we can learn a lot about the end behavior as x approaches negative infinity, as x approaches infinity, and what the graph's kind of going to turn and look like just by knowing what the leading coefficient is based on what the exponent is and what the sign of leading coefficient is. So here are the 4 different ways that we can look at it by how these things are, by what our leading coefficient is, if it's positive, and what the exponent is. So in this case here, if we have a odd exponent, okay, an odd exponent, and our leading coefficient is positive, then you can just look at what the graph is going to look like here, and also just kind of point out what you see with the limits. You're going to have kind of going to start down here with negative infinity. As it approaches negative infinity, the limit is going to be negative infinity, and then you're kind of work your way up where it's positive infinity. Okay, just the opposite if your leading coefficient, your a sub n, your leading coefficient, if it is negative. So again, we're dealing with an odd exponent. So 3, 5, whatever going on, and then you have a negative exponent, or sorry, negative low leading coefficient. Okay, so again, we're looking at the power and the sign of the leading coefficient here. All right, so in that case, we can see that it's a little bit different. Oops, sorry. So again, in this case, you can see it's a little bit different because it's kind of flipped around. Now, because your leading coefficient is negative, still dealing with the odd exponent, now it's going to be more along the lines of we're going to start as x is approaching negative infinity, we're going to start with positive. So kind of negative, positive, and then it's going to end down here. as x approaches infinity, f of x is going to negative infinity. So you kind of start maybe at whatever way it helps you. Like this one starts low on the left and goes up to the right. Maybe it's a little increasing. Maybe that helps you, right? This one would be more of a decreasing graph because it starts up on the left and then finishes down on the right. Whatever it helps you to remember that, but that's kind of what we're looking at. We can look at what happens with the exponent and the leading coefficient. Now let's change the exponent to an even number. So if our exponent is even, and then we have a positive leading coefficient. So in this case, you can see that it's even, that both of our limits are going to be positive. Both of them are going to be approaching approaching positive infinity in this case. Okay, you can see right here and right here that both end behaviors were going up here and we're going up here. So because your exponent is even, so 2, 4, 6, those powers, and then your leading coefficient is positive, that's going to happen. So just the opposite happens on the other side. When we still have an even exponent, so squared to the 4th power, to the 6th power, so on, and now our leading coefficient is negative, you can see what that does is it's going to make your limits here be down at the bottom, both approaching negative infinity. Okay, so we can kind of just glean that and get that information just by knowing what happens with our leading coefficient. Okay, so let's do some examples with that. All right. And then, so this part here just says describe the end behavior, and we're going to look at describing the end behavior of each graph and using limits. So we're going to use our limit notation, and we'll explain our reasoning using the leading term test. Okay, so we can kind of do that, and it's fairly simple. So we can see that basically you've got an odd exponent. Okay, so that's kind of our reasoning. And then our leading coefficient here is positive. So I can tell just by that, if I look back on the tables here that we looked at down here, I can kind of look at what we've got. We've got an odd exponent, and we've got a positive leading coefficient. So it's going to kind of be this example right in here, right? So I know right away now that the limit of f of x as x approaches negative infinity is going to be negative infinity. And I also know that it's going to be positive too, right? So limit of f of x as x approaches infinity is equal to positive infinity. And what's my, explain my reasoning? It's basically just saying that n equals 5, n is the exponent, and a of n, that's, remember, our leading coefficient. Sorry, just got to finish that up. N equals 5, that's an odd exponent. And a sub n, your leading coefficient, is 4, which is positive. So that gives us all the answers that we need there. Okay? That's basically your rationale for why it happened. All right, so let's look at 2, same idea. So now, in this case, we're looking at these two things. We're looking at the exponent, that's going to be even, and then we've got your leading coefficient of -2, which is negative. So now we're going to have a little bit of different situation. So now going back to this one, we've got even and negative, even and negative. So if we look at even and negative, that's down here. They're both going to be pointing down. The limits will be both approaching negative infinity. Okay? So again, I read it in limit notation. Limit of f of x as x approaches negative infinity, we know it's going to be negative infinity. It's going to be negative infinity for both of them. Limit of f of x as x approaches infinity is also negative infinity. Okay? And our reasoning, again, what is our reasoning? Explain our reasoning. We're going to basically say what our exponent is. N is 6, and that is even. And then the other part is a sub n, which again, that's our leading coefficient. It's another way of saying it, is negative. It's -2, which is negative So we know this thing points down. Okay. So that's kind of how we do the first set of problems there, giving the limits based on the leading coefficient and the exponent. So not so bad. All right, next, this one, we're going to, oops, I skipped over some stuff. Let's go back to it. All right, quartic functions. So these are fourth degree polynomial functions. Okay, fourth degree polynomial functions. And we have, and then we're also another term we got to look at is turning points. This is where it changes from increasing to decreasing and vice versa, or decreasing to increasing, right? So, and here's some graphs to show you a couple different things. They point out the turning point and their relative maximums or minimums, or absolute maximums or minimums. Those are where you see it, okay? Now, cubic functions, we can look and see here on the left-hand side. These first two graphs here are cubic functions. And on the right-hand side, you can see these are some typical quartic functions. Okay, fourth degree polynomials. So we just want to make sure we understand this part, this paragraph right below. You look at the number of x-intercepts for each graph here. So if we look at on these ones, we can see we've got 1, 2, 3 of them on a cubic function, and then at most 3, right? That's the most we're going to have. And over here, you can see we have 1, 2, 3, 4 on these quartic functions. Now, it's not always going to be the case, because you can see here we have a quartic function with only 2, and you can see here we only have 1 x-intercept on that one. But because the x-intercept corresponds to a real zero of the function, down below is what it says, you can have at most 3 zeros in a cubic function, and your quartic function can have at most 4 zeros. So they could at most, meaning they could have less, like we just pointed out, right? This has 2, and it's a quartic function, but only has 2 zeros, or 2 intercepts, and some of them have 4. And we also pointed out that this one has 1 here, but at most, it can't have more than 3 if it's cubic. It can't have more than 4 if it's quartic. All right, so continuing on to our next key concept is talking about zeros and turning points. So we know now, we can also say, because of that information, that a polynomial function of degree, if degree is greater than or equal to 1, it has at most n distinct real zeros, and at most n minus 1 turning points. So whatever the degree is, that's how many distinct real zeros it could have at most. It could have less, but at most that many. And then n minus 1, so the degree minus 1 would be how many turning points you would have. So in a quartic, it could have 4 zeros and 3 turning points. In a cubic, it could have 3 zeros and 2 turning points. All right, so a couple things just to also keep on note, and just look at this, just to review so we know that what we're talking about as we review some stuff. So understand that if we've got a polynomial and c is an x-intercept, so we know again that we're saying that c is an x-intercept of the graph, then we can say the following things, that c is a zero of that. So zeros, intercepts, solutions, remember those are all kind of the similar things. X equals c is a solution of the equation, okay? And also x minus c is a factor of the polynomial. So let's just kind of write some real number examples. Let's say I factored something and I got, a factor of x minus 2, x plus 3, right? So when we look at those are factors. So I could just say this x minus 2, that would be this part here. It's a factor of the polynomial. And then we went to solve it. We could say, x minus 2 equals 0. So x equals positive 2. That would be x equals 2. That would be this part here. That's a solution. And then we would say that this 2 here, 2 is a 0 of it because it would cross the intercept at x-intercept, x-axis at 2. Okay? So when we use real numbers, that's kind of what we're saying. But all those things can be true. All right, so how do we do these? How do we find these? So we're going to have to work on some factoring. So state the number of possible zeros and turning points these have. We'll know that just by looking at the leading degree. And then we can also factor and find the zeros. So then determine the zeros by factoring. So a couple things we're doing here. Number one, we're stating the number of possible real zeros and turning points of that equation. Oops, and we're actually not. We're going to use these other two equations. So cross this out. We don't need that. Okay. Of these two. And then, so we're going to do one thing there. We're going to determine that. That's one. And then the second thing we're going to do is determine the real zeros by factor. Okay. So first, let's look how many zeros are we talking about. So in this case, we know because of this degree, again, I can look here and say because of this, because of that, I know that my zeros have to be at most 3. So the zeros have to be less than or equal to 3. Okay. And then I can also say that n minus 1 is 2. So the most turning points we could have is 2 turning points. Okay. And so the next part would be to actually solve this thing out. Okay, and factor it and then find the zeros. So to do that, remember, we want to set equal to 0 and factor. Set equal to 0 and factor. Okay, so let's do that. We've got x cubed. That's what we're starting with, x cubed minus 6x squared minus 27x. So I'm going to set that equal to 0 so I can factor it. And now I know I can see I can pull an x out. I can factor out an x. So I have x squared minus 6x minus 27. And that's going to equal 0 here. And so now in the parentheses, I can factor. Still got my x outside, and inside it's going to factor 2x minus 9, x plus 3 equals 0. So now I know that my zeros are going to be 0 for that one here, 9, and negative 3. Okay. All right, let's try the next one. Okay. So again, you know what? I'm going to actually save this one for you guys. If you guys can solve that one, save that one, that will save some time, because basically the same thing. Look to how many turning points, how many zeros, and then look to factor. Okay. So that way we can move on. All right. So we can also use factoring techniques, right? Even if it's in the quadratic form. And so let's talk about the quadratic form and what happens here. So in this case, a polynomial we would say is in quadratic form if it is written in this form, au squared plus bu plus c. If it's written like that for any numbers a, b, and c, where a can't be 0, and use some expression of x. What does that mean? It means just think about, in this case, think f of g of x. Remember when we did that, we had to plug in g of x into the f function. We're kind of doing that. U is some expression in x. Okay, so what we're thinking here is if you got a symbol x to the 4th minus 5x squared minus 14, it's in quadratic form because we could rewrite it like this, where basically u equals x squared. And that's what I'm telling you to think about this part here. Think f of g of x, where you're plugging in x squared for your u's. Okay, then it becomes u squared minus 5u minus 14. So let's do just that. Okay, so let's show you the step-by-step process on how to do it, and then we'll work on it. Okay, so set the polynomial equal to 0. That should be our first step. Set this equal to 0. Okay, then rewrite the expression in terms of a quadratic function. So we want it in quadratic form. Okay, now we're going to substitute some things in. Here's we're going to say let u equal x squared. Then we can go ahead and factor. And then we want to replace x squared back in for u and solve for x. So a lot of stuff here, but it's basically factoring, and then you might have like 1 or 2 extra steps. So let's practice down here. So let's see where we're at time-wise. Okay, we're getting close on it. Okay, so let's take a look. If we do this one, so the first thing I want to do is look at, it says state the number of possible real zeros and turning points. So again, canceling this out, we're not doing this one, we'll do the other two, okay? So I'm looking at that leading, the degree of this is 5. So my zeros, I know can be less than or equal to 5. And that means my turning points would be 4. Okay. All right. So now let's go ahead and try to factor this out. So we set that equal to 0. I'm going to actually factor out the x as well. So x times x to the 4th minus 6x squared minus 16, and set that equal to 0. All right. So here's where we talk about doing this part here, step 3, substituting u in for x squared. Now, where we see the x squared, because I can kind of rewrite it here, because I can rewrite it in this form, I can say x squared squared, right? Because that would be x to the 4th minus 6, and I'm just putting it in parentheses because of the next part, minus 16 equals 0. Gotta close that bracket down. And now if we look, it says, well, again, replace, let u equal x squared, and then we can use it as a quadratic, or we can factor it, right? So as I continue on here, all I'm going to do is where I see an x squared, I'm going to plug u in for. So I've got x outside, and now I've got u squared minus 6 times u minus 16 equals 0. And I'm just pointing that out one more time. All I did in this step here is basically let u equal x squared. So I'm subbing it in here and here, okay? Now this is easily factorable, because then I can go ahead and continue this on, and I can say, well, x stays on the outside. This thing can be factored into u minus 8, u plus 2 equals 0. And now here's where I do the last part, where I factored it, and now I'm doing this part here, where I'm going to replace x squared back in for u and solve for x. Okay, so by doing that, I'm going to have x here. So now, like I said, what I'm doing is now I'm basically saying let u equal x squared, or x squared equals u. So I'm plugging those in here and here. So now I'm going to have x times x squared minus 8 times x squared plus 2 equals 0. And now I can go ahead and I can factor these out and solve. Okay, so over here, I'm going to look at x equals 0. We're good there. On this one here, I've got x squared minus 8 equals 0. So I add 8 to both sides. So now I have, what is that? Square root of 8. So positive negative 2 times the square root of 2 when you go in radical form. Okay. And then we have x squared equals, let's say plus 2 equals 0. X squared equals negative 2. Now when I want to take the square root of both sides, I can't, right? That's a negative number, so that's no good. That equals bad. Nope, can't do it. So now I know that my only answers are right here. 0 and positive negative 2 times the square root of 2. Okay? Okay, so because we're over 20 minutes, I'm going to let you try number 6 on your own. We can work on it in class as well. We'll kind of look at that in class on that one, and we'll let you figure that one out. Okay? So stop there. You've got 2 problems to kind of do on your own. I just didn't want to do another one because we're at 25 minutes already. All right? Bring your questions. We'll work on these in class tomorrow.